Welcome back. In this lesson, we're looking at generative models and machine learning. AI/machine learning educational explainer. Now let's look at introduction. What if a machine could create a new image, write a paragraph, compose music, design a molecule, or generate realistic data? That is the main idea behind generative models and machine learning. Unlike systems that only classify or predict, generative models can create something new. They learn patterns from existing data and then produce new examples that look similar to the original data. This is why generative models are behind many modern AI tools. In this video, we will understand what generative models are, how they work, their major types, key architectures, applications, and how they differ from discriminative models. Now let's look at detailed definition of generative models. A generative model is a machine learning model that learns the underlying pattern or probability distribution of data. In simple words, it studies examples and learns what makes those examples look real. After learning, it can generate new data that has similar structure, style, or behavior. For example, if it learns from thousands of cat images, it may generate a new cat image that did not exist before. If it learns from human-written text, it can generate new sentences, explanations, or stories. The important point is that generative models do not simply copy, they learn patterns and use those patterns to create new outputs. Now let's look at why generative models matter. Generative models matter because they move AI from only understanding data to creating data. They can help humans write, design, simulate, test, imagine, and explore. They are useful when we need new examples, creative content, synthetic data, or possible future scenarios. For businesses, they can support automation, personalization, and innovation. For scientists, they can help discover molecules, simulate systems, and analyze complex patterns. For learners, they show one of the most powerful ideas in modern artificial intelligence. Now let's look at core concept 1, data distribution. To understand generative models, we first need to understand data distribution. A data distribution describes how data is spread and what patterns are common. For example, human faces have common patterns such as eyes, nose, mouth, and facial structure. A generative model tries to learn this hidden distribution from examples. Once it learns the distribution, it can create new examples from the same pattern. This is why a model trained on faces can generate new realistic faces, and a model trained on text can generate new meaningful sentences. Now let's look at core concept 2, latent space. Latent space is a hidden mathematical space where the model stores important features of data. Think of it as a compressed map of meaning. For images of faces, the latent space may represent features like age, smile, hairstyle, lighting, or face angle. For text, it may represent meaning, tone, grammar, topic, or writing style. The model does not store these features like human words, but as numerical patterns. By moving through latent space, a generative model can create different but related outputs. Now let's look at core concept 3, sampling and generation. Once a generative model has learned a data pattern, it can generate new outputs by sampling. Sampling means choosing a point or possibility from the learned distribution. The model then converts that sampled point into an output such as an image, sentence, sound, or video frame. This is similar to a musician who learns a style and then creates a new song in that style. The new output is not a direct copy of one example. It is a new creation based on learned patterns. Now let's look at core concept 4, training objective. Every generative model needs a training objective. A training objective tells the model what it should improve during learning. Some models try to reconstruct the original input as accurately as possible. Some models try to fool another model into believing generated data is real. Some models learn by gradually removing noise from data. Some models learn to predict the next word, token, pixel, or signal. Different training objectives lead to different generative model architectures. Now let's look at main types of generative models. There are several important types of generative models. Autoregressive models generate output step by step, such as one word after another. Variational autoencoders learn a compressed latent representation and generate new examples from it. Generative Adversarial Networks use two models that compete with each other. Diffusion models learn to create data by starting from noise and gradually refining it. Flow-based models learn reversible transformations between simple distributions and complex data. Each type has strengths, limitations, and common use cases. Now let's look at autoregressive models. Autoregressive models generate data one step at a time. In text generation, they predict the next word or token based on previous words. For example, after the phrase "machine learning is," the model may predict words like powerful, useful, or important. This step-by-step process continues until a complete output is formed. Autoregressive models are widely used in language generation and sequence prediction. Their strength is that they can produce coherent sequences, but they may be slower because they generate one step at a time. Now let's look at variational autoencoders. A variational autoencoder, or VAE, is a generative model that learns to compress data and then rebuild it. It has two main parts, an encoder and a decoder. The encoder converts input data into a compressed latent representation. The decoder takes that latent representation and reconstructs the data. After training, the model can sample from the latent space and generate new outputs. VAEs are useful for representation learning, anomaly detection, image generation, and creating smooth variations of data. Now let's look at Generative Adversarial Networks. A Generative Adversarial Network, or GAN, uses two neural networks. The first network is called the generator, and it creates fake data. The second network is called the discriminator, and it tries to detect whether the data is real or fake. The generator improves by trying to fool the discriminator. The discriminator improves by becoming better at catching fake examples. This competition can produce highly realistic outputs, especially images, but GANs can be difficult to train. Now let's look at diffusion models. Diffusion models are generative models that learn by adding and removing noise. During training, clean data is gradually turned into noisy data. The model then learns how to reverse this process. During generation, the model starts with random noise and slowly transforms it into a meaningful output. This approach is very powerful for image generation and is also used in audio, video, and scientific applications. The key idea is simple: start with noise, then refine it step by step. Now let's look at flow-based models. Flow-based models generate data using reversible mathematical transformations. They start with a simple distribution, such as a normal distribution. Then they transform it step by step into a more complex data distribution. Because the transformations are reversible, the model can move both ways, from data to latent space and from latent space to data. Flow-based models are useful when we need exact probability calculations. They are less commonly discussed than GANs or diffusion models, but they are important in advanced generative modeling. Now let's look at transformer-based generative models. Transformer-based generative models are especially important for text, code, and multimodal AI. They use a mechanism called attention to understand relationships between different parts of input data. In language models, transformers learn how words and ideas connect across a sentence, paragraph, or document. They can generate text, summarize content, answer questions, write code, and support chat-based AI systems. Modern generative AI tools often use transformer-based architectures. Their strength is handling context and generating coherent, flexible outputs. Now let's look at Application 1, Text Generation and Chatbots. One major application of generative models is text generation. These models can write explanations, emails, stories, summaries, product descriptions, and code. Chatbots use generative models to understand a user's request and produce a helpful response. In education, they can create study notes, quizzes, examples, and tutoring support. In business, they can draft documents, analyze customer queries, and support knowledge work. The key benefit is that they can generate human-like language at scale. Now let's look at Application 2, Image Generation and Editing. Generative models can create new images from text prompts, sketches, or reference images. They can generate illustrations, product mock-ups, educational diagrams, design ideas, and artistic visuals. Image editing models can remove objects, change backgrounds, improve quality, or transform styles. This is useful for designers, educators, marketers, creators, and researchers. In education, image generation can help explain abstract concepts visually. However, image generation should be used responsibly to avoid misinformation or misleading visuals. Now let's look at Application 3, Audio, Music, and Voice Generation. Generative models are also used to create audio, music, and synthetic speech. They can generate background music, sound effects, voiceovers, and speech in different styles. In accessibility, voice generation can support people who need assistive communication tools. In education, audio generation can help create narration, pronunciation examples, or language learning content. Music generation can help creators explore melodies, rhythms, and arrangements. Responsible use is important because voice generation can also be misused for impersonation. Now let's look at application 4, video and animation generation. Video generation is one of the most advanced applications of generative models. A video is harder than a still image because it must maintain consistency across time. The model must understand motion, objects, lighting, background, and scene continuity. Generative video tools can help create animations, simulations, educational clips, and concept demonstrations. They can reduce the cost and time needed to produce visual content. Still, video generation requires careful review because small errors can appear across frames. Now let's look at application 5, healthcare and drug discovery. In healthcare, generative models can support research, diagnosis assistance, and drug discovery. They can help design new molecular structures that may become potential medicines. They can generate synthetic medical data for research when real data is limited or sensitive. They can also help enhance medical images or simulate possible biological patterns. These applications require very careful validation because healthcare decisions are high risk. Generative AI can assist experts, but it should not replace professional medical judgment. Now let's look at application 6, synthetic data and data augmentation. Generative models can create synthetic data, which means artificial data that resembles real data. This is useful when real data is limited, expensive, private, or imbalanced. For example, a model can create more examples of rare defects in manufacturing images. In machine learning, synthetic data can help train models more effectively. Data augmentation creates modified versions of existing data, such as rotated images or rephrased text. However, synthetic data must be checked carefully to avoid bias, errors, or unrealistic patterns. Now let's look at application 7, design, simulation, and creativity. Generative models are useful in design and simulation. They can help create product designs, building layouts, game assets, fashion concepts, and engineering options. Instead of manually testing every idea, designers can explore many possibilities quickly. In simulation, generative models can create possible scenarios for planning and analysis. This helps teams brainstorm, prototype, and improve ideas faster. The best results usually come when human creativity and AI generation work together. Now let's look at generative versus discriminative models. Generative models and discriminative models solve different types of problems. A discriminative model focuses on separating classes or predicting labels. For example, it may classify an email as spam or not spam. A generative model tries to understand how the data itself is formed. For example, it may generate a new email that looks like a real email. In simple terms, discriminative models answer, "What category is this?" while generative models answer, "What could a realistic example look like?" Now let's look at strengths and limitations. Generative models are powerful because they can create new content and support creativity, automation, and research. They are useful for text, images, audio, video, data generation, and scientific discovery. But they also have limitations. They can produce incorrect, biased, unrealistic, or misleading outputs. They may require large datasets, high computing power, and careful evaluation. That is why human review, responsible design, and ethical use are very important. Now let's look at recap and closing. Let us quickly recap. Generative models learn patterns from data and create new examples based on those patterns. They use important ideas such as data distribution, latent space, sampling, and training objectives. Major types include autoregressive models, VAEs, GANs, diffusion models, flow-based models, and transformer-based models. They are used in text, images, audio, video, healthcare, synthetic data, design, and simulation. The key difference is that discriminative models classify or predict, while generative models create. If this explanation helped you, like, share, and subscribe for more simple lessons on AI and machine learning. To wrap up, here is the key takeaway. You now have a structured overview of generative models and machine learning. Review the core ideas, connect them to examples, and revisit concepts like introduction, detailed definition of generative models, why generative models matter when practicing. If you can explain the idea in your own words, you have really understood it.